Good afternoon. My name is Donát Takács, and today I will present a paper called Maintenance Schedule Optimization for Manufacturing Systems. The presented work has been carried out in the EU-funded programs project, which has been already introduced in its entirety in the previous presentation by Mr. Suriko. In the next 15 minutes, first I will present the motivation behind this research and our goals. After that, I will introduce the basic assumptions we had regarding the investigated manufacturing systems. Next, I will present the logical structure of the research and our approach to maintenance optimization. Then, I will list and present all of the software components which are parts of the optimization process. After that, I will briefly mention some implementation details, and finally, I will end my presentation with the conclusions. So, what are our motivations? Our ultimate goal is to provide support to plant managers in implementing smart and cost-effective maintenance solutions. In order to achieve this, our research focuses on maintenance optimization to provide the optimal maintenance strategy, labor policy, and prevention schedule for all machine components, which either minimizes cost, maximizes equipment availability, or do both at the same time. Clustering maintenance activities is also considered in order to further reduce costs and the number of machine stops. The presented approach can be used to show whether a predictive maintenance strategy for a specific component is feasible and cost-effective or not. Regarding the investigated system, our basic assumptions are that we have complex multi-component machines and multi-machine systems. These systems can be repairable, but they can also contain unrepairable components. We also assume that the production equipment can be modeled with serial reliability, so that if a component of the machine fails, the whole machine stops. Furthermore, not only perfect and minimal repair, but imperfect maintenance is considered during the analysis. As for the considered maintenance strategies, we have the traditional corrective maintenance, we have the periodic preventive maintenance with component replacement, and the predictive maintenance with real-time condition monitoring. We also have a so-called ordinary scheduled maintenance, which is a periodic minimal repair, for example, cleaning or lubrication, which is not optimized, but the cost associated to it is considered during the analysis. As for the maintenance policy options, we have internal crew policy, we have an external service on an on-demand basis, as well as an external service with an annual framework contract. In the program's framework, the optimization is performed by the Maintenance Schedule Optimization module, MSO for short, which is one of the central hubs of the program's architecture, and it is tightly integrated with the other modules of the program's platform. The MSO itself is composed of multiple software tools. The heart of the module is the optimization engine, which runs the reliability and maintainability simulator and the LCC calculator iteratively. Even though the MSO can be used as a standalone solution, its capabilities can be extended by connecting it to other programs modules, such as the Smart Scheduling tool or the Maintenance Service platform. In the following slides, I will present all of the MSO software tools one by one. The first step in the optimization process is the proper definition of the system and the machines we are working with. The hierarchy of the equipment components is represented by an equipment tree. The tree is built from the system level to component level. Practically, the nodes have to be extended up until we reach the components or component groups, which are maintained as a block. During the further analysis, the direction of flow is exactly the opposite. We have the results on component level, which are then propagated upwards to system level, following a bottom-up approach. In the MSO, for equipment tree creation and manipulation, the so-called tree editing system has been developed. Once we have the machine definition and the list of components, the next step in the process is data analysis. In order to predict the future maintenance-related behavior of the system, we need to know the underlying reliability models and their parameters for each component. These models and parameters are extracted from historical maintenance reports, collected either from legacy databases or from dedicated softwares, such as the program's Maintenance Service platform, following a data-driven statistical approach. However, data quality, quantity, and reliability is often an issue. Even though a precise data collection is preferred, In some cases, only sensor maintenance data is available, which brings uncertainty to the estimation. In the program's MSO, the live data analysis tool has been developed in order to perform the model selection and parameter estimation. A wide variety of models are considered, including different failure distributions and live stress models. The parameters of these model components are estimated jointly. The maximum likelihood estimation method is exploited for parameter estimation, which can handle sensor data and also makes automatic model selection possible based on the likelihood values. The method can be used to estimate the detection threshold of condition monitoring systems as well, in case a sufficient amount of detection-related data is available. From the reliability model determined by the LDA tool, future behavior of the system can be predicted, as well as the reliability and maintainability parameters, such as availability or total downtime, for a user-defined time horizon. As real manufacturing system can be extremely complex, analytical or numerical approaches are unfeasible in most cases. In order to handle such systems, a discrete event Monte Carlo simulation method is used. In this stochastic approach, the time and duration of maintenance events are generated randomly based on the reliability models. Once we reach the simulation end time, the R&M parameters are calculated. Here the process of the single simulation is illustrated. Here we can see a manufacturing system with 3 machines and 9 components in total. On components number 2, 3, 5, 7 and 9, a preventive maintenance strategy is applied. There is a single worker assigned to perform the maintenance actions on these components. As the simulation time progresses, we can see how the states of machines and components change. As discussed before, we can see that once a component fails, the whole machine stops. We can also see that even components with preventive maintenance strategy can fail, like it happened for the 7th component right here. We can also see that the simulation stops once a predetermined time horizon is reached. Then, the simulation process is repeated multiple times, and the final results will be the average of the individual simulation results. Once we have the R&M parameters, they can be further evaluated to calculate some sort of goodness indicator of the maintenance plan. For profit-oriented firms of the manufacturing industry, the maintenance-related cost is a natural choice for such a purpose. In the framework of the program's project, a realistic life cycle cost model has been developed, which is composed of 2 main cost categories: time-related costs and event or strategy-related costs. The former one can be further divided into the cost of lost production, labor-related costs, and the annual cost of ordinary maintenance. For the strategy-related cost components such as the cost of collateral damages, cost of spare parts, the fixed cooling cost of external services, and the implementation cost of predictive maintenance are considered, but of course only when they are applicable. The optimization of maintenance strategies, policies, and prevention schedules is the main goal of the MSO. The optimization objective can be the minimization of the LCC, the maximization of the availability, or both, which is of course a multi-objective optimization, and can be performed on component, machine, and system level. The optimization process follows a genetic algorithm-based iterative approach. First, an initial population is created either randomly or based on some analytical optimization. Then, these solutions are evaluated with the R&M simulator. Their fitness value or goodness is calculated, which can be either the LCC, the availability, or the combination of these two. The best solutions are kept, a new population is generated, and the process repeats until the predefined number of generations has been reached. The final results will be the solution with the highest fitness value. Here we can see an example for the optimization. At the top we have an initial state, while at the bottom we have the optimized maintenance plan. We can see that not only the total cost decreased, but based on the Gantt diagram, it is evident that the amount of useful operation time has increased as well. On this chart, the best solutions of each generation are displayed. In the optimization process, the clustering of planned maintenance events is also considered. On one hand, if we have many components with different preventive maintenance intervals, The machine stops can be so frequent that it makes the production plan unfeasible. On the other hand, by grouping maintenance actions to be performed at the same time, we can decrease costs by performing common operations, such as assembly and testing, only once. Finally, if there is a fixed calling cost for all maintenance events, the grouping of actions can reduce the total calling costs as well. In the MSO optimization engine, the clustering is implemented as an extension of the genetic algorithm. Since the results of the optimizations are significantly influenced by the starting point of the genetic algorithm, great attention was paid to the determination of the initial solutions. By having a better initial estimate of the solution, either the better final solution can be reached in the same amount of time, or the same solution can be reached in a shorter time than without analytical optimization. With a simplified model, the optimal maintenance strategy can be selected with analytical computations on component level. Although this is not sufficient for final results, it can serve as a starting point of the optimization. Based on the individual prevention intervals, the initial maintenance clusters can be formulated using analytical calculations as well. So, with all of these software tools introduced, I will continue with some implementation details. The MSO, as we have seen, consists of multiple interconnected software tools and thus can be considered a software platform. This software platform is implemented as a web application, which makes it accessible from any browser and any hardware. The MSO architecture is a 4-tier architecture, which is composed of the following layers. First, there is a persistence layer, which is the database behind the application. Then there is the service layer, which contains the web services, responsible, among others, the intermediate communications. The logical layer, where the application logic and the main functionalities are located, are also part of this architecture. And finally, we have the presentation layer, which is responsible for the user interfaces. Of course, in order to provide the feel of familiarity, the MSO web application uses the common program's user interface templates and style sheets. In the slides, we can see the login screen and the optimization engine interface. As conclusions, we can say that the MSO is one of the main hubs of the program's suite of solutions, which aims to provide the optimal maintenance strategies, label policies, and prevention schedules for all equipment components. In order to achieve this, a set of software tools has been developed to cover the whole process from equipment definition and data analysis to simulation, cost calculation, and optimization. Even though the MSO is designed to be functional as a standalone solution, as part of the overall program's platform, the intermodule communications are foreseen to result in further benefits. A 15 to 20% reduction of costs and 30% increase in productivity is expected by exploiting the MSO platform. Unfortunately, these values are still only estimates because of the delayed demo line validations due to the COVID pandemic. Thank you for your attention.